Can't touch this. Can't touch this.
Yep, we are talking some more about limits today.
Can't touch this.
Lesson 2.4. And we're also going to talk about asymptotes. So, okay. You want to be doing this assignment on the same day, or this video on the same day that you're doing 2.3 day 2, because they really are going to go together and they are assigned on the same day. All right, so we're going to be looking at what happens when we've got limits if we have a vertical asymptote in our diagram. And so I also want to review with you guys a little bit on how to graph these rational functions. So if we take a look at the first one, this denominator is important because what's going to happen is along the denominator, if you have domain restrictions along the denominator, and if the factor creating that domain restriction is not actually repeated again on the numerator, then you're going to have a vertical asymptote at the root of that solution. So in this particular instance, there is a vertical asymptote at x equals positive 4. The x equals is important because this is an equation of a line. This is not a point, this is a line. So the x equals is required to be there. As for the horizontal asymptotes can be found by comparing the numerator and the denominator and seeing what grows faster. And usually we talk about degree a lot of the time if we're looking at polynomials. But in general, what we're looking for is to see, is it growing slower on the numerator or on the denominator? And if it's growing faster on the denominator, then what ends up happening is that we would have a horizontal asymptote at y equals 0. So in this particular instance, because 3 is a constant on the numerator, the numerator is actually not growing at all. It's staying at 3. The denominator, though, as I start putting in larger and larger positive values, will become larger and larger. So I'll have 3 over an increasingly large value, which will start to approach 0. So we will have a horizontal asymptote at a height of 0. The general form, the parent function for, let's see if I can get this, the parent function for all of these rational functions is y equals 1 over x. And the graph of that looks like this. It has a horizontal asymptote at y equals 0 because it's growing faster on the denominator. It has a vertical asymptote at x equals 0 because there's a domain restriction on the denominator. And if you plot a few points, it looks like this. In fact, this is our basic form, and then we just want to kind of look and see how things maybe are transformed from that parent function. So basically what happens on this one is we have a 3, which is just going to make our height 3 times higher. Taller, and then, or even shorter in the negative direction. And then we have our vertical asymptote shifted to the right 4 units. And other than that, we really have the same diagram. Now, in any rational function, if you're having a little bit of a hard time sketching it, you could consider just choosing a couple values on either side of the vertical asymptote, substituting them into the function and seeing what you get. And when you substitute in a 3, you get 3. Maybe not, you get negative 3. Let's try that again. So right here. And if you substitute in the 5, you get positive 3. And then we're going to be bounding these curves by the horizontal and vertical asymptotes. Just a note on horizontal and vertical asymptotes, although it is uncommon, you actually can cross a horizontal asymptote, sometimes in the interior portion of a graph, but not on the ends. Vertical asymptotes, however, will never be crossed. You might notice that these two are very similar functions. We just have a shift and a little bit of a stretch. All right, now we can use this graph in order to answer the questions about what's happening on the left and the right side. So as I approach 4 from the left, I'm going down forever. Now I'm going down forever, which would be the idea of negative infinity, but really limits are asking us for a finite concrete number. And negative infinity is the idea that we keep going forever and ever in the direction of negative infinity. We keep having smaller and smaller numbers there, but it's not actually a number. So what we're going to say here is that this limit does not exist. However, we are also going to indicate what direction it's going into. This doesn't exist because it's approaching negative infinity. And so when you guys are doing these problems, I actually want you, and so does Mr. Gannon, we want you to write down both of these answers. Your textbook, I believe, will say negative infinity. College Board typically will say does not exist. We are going to make sure that you guys are writing both. As I approach 4 from the right-hand side, I'm actually going up and up to positive infinity. Again, positive infinity is a concept, not an actual value. And so we're going to say this limit doesn't exist, but it is the reason it doesn't exist is because it's going to positive infinity. And that's a required portion of your answer for this class. If I look at the two-sided limit, we are going to 2 different directions. And since we are having different behaviors on the left and the right side, we're going to say this does not exist. And we're not going to put positive or negative infinity because the behaviors are different. So if the behaviors are different, you will only exist. Whoa, didn't mean to do that. Thought I was highlighting there, sorry. It is mad at me now. And let me do stuff. Awesome. This does not exist. All right, I'm going to have you pause the video after that awesomeness and take a look at example 2. Try to think about that graph. How would that graph differ from the 2 functions we were just exploring? See if you can sketch this and then restart the video when you're ready. For number 2, what I'm noticing here is, first of all, there is this negative multiplier here, which a negative multiplier is going to cause a vertical reflection. So I'm thinking we've got some things that are flipped over the x-axis and turned upside down. I'm noticing also that the vertical asymptote's in a different spot, and I also notice that this is squared, which is going to change some signs for us a little bit. So I do want to pay attention to that. All right, I usually start by graphing the asymptotes. The vertical asymptote here is going to be at x equals -2. And for the horizontal asymptote, again, we have a higher degree on the denominator, so this is growing slower on the top. It's actually staying the same, it's a constant, but it's growing faster on the denominator, so the horizontal asymptote is at y equals 0. Again, asymptotes are lines, so you need to write them as equations and not just as numerical points. If we wanted to, we could stop and test a couple values here, although it might be worth a moment's time to just look at the signs that'll be happening with this equation. On the numerator, I have a constant of -3, so no matter what, I will start with a negative on the numerator. On the denominator, I'm squaring this binomial, so I will always end up with a positive. And a negative divided by a positive is always a negative. So what this means is that I have only negative outputs, and I should be below my x-axis no matter what. So I'm suspecting that these will look something like that. And I'm going to test a couple values just to verify that, since it's been a while since you've done rational functions. And I'm going to test some values on either side of the vertical asymptote. And so if I substitute in a -1, I'd have -3 over +1 squared, which is -3. And again, I'm going to fit this to curves. And if I test -3, I have -3 over -1 quantity squared, and -1 times itself would revert back to a +1, and after I divide, end up back to -3 again. And so my suspicion about these both being below the x-axis was correct, and there's my graph. As I'm looking at the limit, as I approach -2 from the left-hand side, I am going down to -infinity, which is not a numerical finite value, so I'm going to put does not exist because we are going in the direction of -infinity. As I approach -2 from the right-hand side, I'm also going to -infinity, which is not a finite value still, and so that does not exist because I'm approaching -infinity. As I look at the two-sided limit, I'm actually have the same behavior on both the left and the right-hand side. I'm still approaching -infinity, but I'm going to approach -infinity on both sides, and so I'm going to actually specify for this answer does not exist because I'm approaching -infinity. I'm doing a video, but I'm going to be done with it in about 5 minutes, if that's okay. I'm so sorry. Hi guys, I have visitors in my class here right now. No worries.
It's okay, we'll come back.
Okay. sounds good. Sorry about that. Do you want them to sing for you? We did have Can't Touch This up here. We had some music, so that was good. All right, for number 3, why don't you go ahead and pause the video and see if you can remember how to graph tangent. If you had forgotten how to graph tangent, it might be helpful to remember that tangent of x is the sine of x divided by the cosine of x, and that can help us in terms of our asymptotes. Cosine of x would be where our vertical asymptotes are going to occur where the cosine of x is actually equal to 0. So we will have vertical asymptotes where cosine of x is equal to 0. And if I think about the unit circle, that is a semi-decent circle. Remember, the cosine is our x values. So we have x values that are 0 up at pi over 2 and at 3 pi over 2. And so we will have vertical asymptotes at x equals pi over 2, x equals 3 pi over 2, and so forth, including negative pi over 2. That would just be going in the opposite direction, and so forth. I'm not going to worry too much about all of them because my point of interest here is pi over 2. So I'm just going to draw a portion of this periodic graph. So at pi over 2 and at 3 pi over 2, I am going to have vertical asymptotes. I also have more. I could write one at negative pi over 2 if I wanted, if that was helpful. In terms of a horizontal asymptote, it doesn't really make sense to talk about a horizontal asymptote in this situation because of the way that sine and cosine oscillate between heights of 1 and negative 1. So there's not actually going to be a horizontal asymptote in this particular graph. But it is helpful to see perhaps where would we have x-intercepts. So the x-intercepts are going to occur where sine of x is equal to 0, our numerator. So sine of x is equal to 0 where, since sine is the y-coordinates, where we have a height of 0, which would be at 0, pi, and so forth. So y equals 0, y equals pi, and so forth. So here, here. And then if we wanted to graph this, we could pick a couple values to graph this. There's also a little acronym. Tangent starts at Texas, ends at New York. So we start, or you could even say like Tijuana, it's more on the left side of the graph. The left side, we're starting down at the bottom, and then we're moving up to New York up here at the top. That's tangent. If you don't want to use that, you could also think about the signs. In this region right here, we're in really the first quadrant of our graph. Positive for both sine and cosine. A positive divided by a positive, as we do sine divided by cosine, will give you a positive output. This region is in the fourth quadrant, which would have a positive cosine and a negative sine. And when you divide a negative divided by a positive, we will get a negative. And then this keeps replicating since it is periodic, and so forth. And now that we have a sketch, we can go ahead and graph this. I want to look at pi over 2 approaching from the left-hand side, and that is going up to positive infinity, oh my gosh, which is not a finite number, so it does not exist for the limit. If I look at what's happening as we approach pi over 2 from the right-hand side, I am going down to negative infinity, again, not a finite number. So it does not exist because we're approaching negative infinity. Please make sure you are including the positive or negative infinity. And then as I look at the two-sided limit, the left and the right-hand behaviors are different. We're just going to write does not exist only. We do not include the positive or negative infinity when the behaviors are different. So as a reminder, the vertical asymptotes are going to be factors. You're going to see them from the factors on the denominator that are not repeated in the numerator, and you want to look at that root.